Hello, thank you for watching this recorded talk. This paper is about best response dynamics in lottery contests. This is a joint work with my PhD co-supervisor Paul Goldberg. Please email me if you have any questions. Contests are games where a set of agents compete by putting costly and irreversible investments to win valuable prizes. The two popular and classic models in contest theory are first the lottery contest, which is also known as the standard luck contest, and the all-pay auction. In this paper, our focus is on lottery contests. In a lottery contest, there is a prize, let's say of unit value. There are n agents. Each agent produces a certain amount of non-negative real output, which we denote by xi. So agent i's output is denoted by xi. The allocation of the prize is proportional to the outputs. In particular, agent I gets a prize of xi divided by the sum of xj values, that is the total output, divided by the total output. Each agent also has a linear cost. Agent i's cost coefficient is denoted by ci, and the cost that agent I has is ci times xi. The utility function has a standard form where utility of agent I is the price that the agent I gets minus the cost that the agent I bears. Let's look at an example. Say there are three agents. Each agent produces a certain amount of output, which we denote by xi. The price is allocated proportionally. So if the total price is of value 20, then the first agent who produces an output of 2 gets a price of 2 by 6 times 20, and where the total output is 6. Each agent also has a cost coefficient denoted by ci, and the cost that agent I has is ci times xi, as shown in the slide. The utility is the price that the agent gets minus the cost. There are numerous applications of lottery contest. The seminal work by Tulloch used lottery contests to model rent seeking. It has also been used to study political lobbying, research and development races, and more recently, blockchain applications like Bitcoin mining. In this paper, our focus is on studying best response dynamics in lottery contests. And in particular, by best response, we mean the action of for the best response of agent I is the action that gives agent I the maximum utility given the actions of other agents. So if everyone else is playing x minus I, as denoted in the slide, then the action that maximizes ui is the best response. The best response dynamics starts from an initial output profile or an initial state, and then at each time step, one of the agents makes a best response move. So if agent I makes a best response move at time t, then at time t, and then agent I replaces her current action xt I by the best response action given the action of every other agent. And so at each time step, one of the agent moves, and this is the dynamics we study in this paper. Now, how the agent I who is playing the action at time t gets selected. So for two agents, we assume that the agents alternate. It does not make too much sense to study any other scenario because an agent making two consecutive best response moves is redundant. For three or more agents, there are at least two agents who can make a non-trivial best response move at each time step. So we need to have a model for selecting the agents at each time step. We model this using we have a randomized model for this. We assume that the agent I gets selected at time t with certain probability PIT, which can depend upon the output profile at time t as well. For the purpose of this talk, let's assume that at each time step, all the agents have equal probability of getting selected. We select the agents uniformly at random. Let us jump to our results. For homogeneous agents, that is when all the agents have the same cost function, for two agents, we show that the best response dynamics converges to an epsilon approximate equilibrium in log 1 by epsilon plus log 1 by gamma steps, where gamma is a function of the initial state or the initial output profile. Generally, it's the smallest positive output in the initial output profile. This bound is tight up to added constants. For three or more agents, we have a lower and an upper bound. So with respect to gamma, which depends upon the initial state, our lower and upper bounds have the same dependency of log 1 by gamma. With respect to n, also our bound n, which is the number of agents, our bounds, lower and upper bounds have the same dependency, n log n. With respect to epsilon, although our lower bound has a log 1 by epsilon dependency and upper bound has a log 1 by epsilon dependency. Unfortunately, for non-homogeneous agents, best response dynamics may not converge. We provide simple examples where this happens. On the slide, we have an example where the second agent has a cost which is 10 times less than the first agent for the same amount of output, or the first agent has a 10 times higher cost for producing the same amount of output. We get a cycle which takes only 6 steps, as shown on the plot using red color. We can also notice that the cycle is far away from the equilibrium point, which is at the bottom right corner of the plot, denoted by a star. This non-convergence result is also generic, which means that uh, in the space of valid output profiles, the set of starting points and the examples that lead to cycles have a positive measure. For the rest of the talk, I will provide some intuition about our rate of convergence analysis for 3 or more agents, 3 or more homogeneous agents. Let's fix some notation. I will denote the output at time t, output profile at time t by xt, and the output produced by agent I at time t by xti. The total output is denoted by st. The total output of all agents except agent I is denoted by st minus I. Now, using this notation, we can write the utility function as xti divided by sum over j xtj minus xti. Now, remember that we are looking at the scenario when all the agents are homogeneous. And without loss of generality, we are assuming that the cost coefficient, the ci value, is 1 here. One more thing to notice about the utility function is that it depends upon the output of agent I, denoted by xti, and the total output produced by all the other agents, denoted by st minus I. In particular, it does not matter which other agent is producing how much output. For an agent I, what matters is how much total output is being produced by all the other agents on an aggregate. To emphasize this, we will write the utility function as the output of agent I and the total output of all the other agents, st minus I. Another thing to notice is when the total output is 0, then the utility function as shown on the slide is not well defined because the denominator is 0. Also, the allocation function itself is not well defined. Now, in the literature, the usual assumption is that when the total output is 0, either the price is distributed equally among all the agents, or the price is not allocated to any agent. So everyone gets 0. All the agents get 0. For both these cases, there is a discontinuity at 0 when everyone is producing a 0 output. We will look into this issue more in subsequent slides. Okay, the best response function, which we already have discussed before. Now, for this homogeneous case, where the cost coefficient of all agents is assumed to be 1, the best response of agent I, given the total output of all the other agents, st minus I, is as shown in the plot. So the best response function is a smooth curve between 0 and 1. At 1 and 0, there is at 0 there is a discontinuity, and at 1 it's not a discontinuity, but the best response dynamic is not differentiable, the best response function, and it goes to 0 for if the total output by all the other agents is 1 or above 1. To summarize, the good case where the best response function is well behaved is when the total output of all the other agents is strictly between 0 and 1, and in the other cases it does not behave smoothly. It might not. Now, for this special case, when for homogeneous agents, the equilibrium profile, in the equilibrium profile, the output of agent I is given by output of every agent is equal to n minus 1 by n squared, when n is the number of agents, and the total output is n minus 1 by n. Okay, now, given these preliminaries, let's look into the analysis part. So in the analysis, we use a potential function, which is called the best response potential function. Best response potential games are generalizations of ordinal potential games and exact potential games of Monroe and Shapley. We have a potential in a best response potential game. We have a potential function f, where given the output of every other agent, given the action of every other agent, the action that optimizes the potential function for agent I is the same action that optimizes the utility function of agent I, given the same action of all other agents. In particular, what we mean is that the utility function and the potential function have a correspondence with respect to the best response action. In this paper, we use the notation that we are trying to minimize the potential function. Now, this is what the best response potential means. And in this paper, we show when the total output of all the other agents, except of any particular agent I, is strictly between 0 and 1, then the action of the best response action of agent I has this form where it corresponds to the minimizing a potential function, f. So we show the existence of a best response potential function in this special restricted domain of outputs. And this potential function is based upon the work of Erhard. Our potential function also has this property that the potential function f is always non-negative for all valid action profiles, and it it is equal to zero only when the action profile is the same as the equilibrium action profile, or when the total output of all the agents is zero. Let us look at the steps in the proof at a very high level. First, we have analysis of a warm-up phase. So this part of the analysis is to handle corner cases like best response to zero and some other similar corner cases. Then the second part of the analysis is to prove that the potential function f very rapidly converges to zero, which we'll discuss further in the next few slides. Then once we have proven this, that the potential function is going to zero, using strong convexity of the potential function near the equilibrium, we will show that the equilibrium, the action profile is also going towards the equilibrium profile. And finally, if the action profile is close to the equilibrium profile, then using continuity of the utility function, we show that we are at an epsilon approximate equilibrium. Let's take a small detour and talk about something called coordinate descent. Let's say we have a convex function gx. I have plotted a simple convex function on this slide. On the left side, we have a surface plot of g. On the right side, we have the contour plot of the same function. Now let's say we start from a point in the domain, in the xy domain in this example, near 0, 1. From this point, let's say we fix the x coordinate and we find the value of across the y-axis, which minimizes the function g. And then we reach a point, and then from this point, we fix the y coordinate, and then we optimize over the x coordinate. And we repeat this process. So this process is something called the coordinate descent. We can notice that this coordinate descent dynamics minimizes the function g, and eventually it should reach the minimum value of g. Because even if we fix one of the coordinates along the value along one of the axes, still in the domain for all the other coordinates, the function g is still a convex function. So even in this restricted hyperplane, we have the function g is convex, and in that convex hyperplane, we are optimizing. We are getting the minimum value, so we are decreasing the function g, and we repeat this process. And if we repeat this process for all coordinates, then go on, then we will minimize the function g. Now, why this is relevant to our paper? Because if we observe the best response dynamics, there also we have something similar going on. At each time step, all the agents except an agent I keep their output fixed. So and this agent I, with respect to the best response potential function, finds the point which maximizes its utility or minimizes the potential function. So this best response dynamics has a correspondence to this coordinate descent. Now, as we saw in the previous slide, if the function is convex, this coordinate descent should converge to the optimal point, to the minimum of g. Now, although the function f is not convex in the domain of the output profiles, what we can show is that if the total output, denoted by st, is between 1/4 and 1, then f is alpha strongly convex, where alpha is some constant independent of all the parameters in our model, and beta is and f is also beta smooth, where beta is theta of n. Now, using the above properties and using techniques similar to the analysis of gradient descent for smooth and strongly convex functions, we can show that the expected value of this potential function f in this restricted domain, when st is between 1/4 and 1, decreases by a factor of 1 minus some constant times alpha by beta times the expected value of this potential function at time t. And as alpha is a constant and beta is proportional to n, so we get that the expected value of the potential at time t plus 1 is equal to 1 minus some constant divided by n times the expected value of the potential at time t. Now, if we have this result, we can show using concentration bounds that the potential function will become less than epsilon with high probability. But as I said before, F is not convex in the entire domain of output profiles. If in particular, so if the total output is between 0 and 1 by 4, F is not convex, the descent algorithm may not converge. The But what we can show is that if we make a best response move, we do not increase F. So we have a weaker condition that the potential function never increases. It may or may not decrease, but it never increases. Now, to summarize what I've been saying in the previous slides, we can divide the domain of all output profiles into three regions. The outermost region is denoted by blue here, corresponds to the warm-up phase where we do not have much control over the potential function F. So F may even increase in this region. But what we can show is that the potential function F, so the warm-up phase, the best response dynamics does not stay in this region for too long. With high probability, it gets out of this blue region and gets into the white region. Now, inside this white region, where ST is between 0 and 1, is sufficiently small, the potential function F never increases. It may or may not decrease rapidly, but it never increases. On the other hand, there's another region denoted by green, where ST is greater than or equal to 1 by 4. And the equilibrium point is also inside this green region. Now, when the potential function F is in this region, it decreases rapidly. Further, what we can show is that the potential function visits this green region frequently. So it visits this green region frequently, where it decreases rapidly. And when it is in the white region, it just never increases. So after sufficiently many steps in the green region, the potential function goes close to 0. Okay, so how do we show that the potential function F visits this green region, or when the total output is above 1 by 4 frequently? So what we do is we discretize the space of the output ST. And in particular, we have a double exponentially decreasing regions. So one of the regions is, so as we can see at the bottom of the slide, I have a Markov chain. So the leftmost state corresponds to ST values, which are above at least 1 by 4. In the next state, it is between 1 by 4 and 1 by 8, 1 by 8 to 1 by 32, and so on. So it is a double exponentially decreasing values of the output. Now, what we can show is after the warm-up phase has finished, that the total output ST moves left as per this Markov chain with probability 1 minus 1 by n, and moves at most one step right. It can stay at where it is, or it can move at most one step right with probability 1. Now, using this, what we can show that starting from any initial total output S naught, which is equal to gamma, we will reach ST greater than or equal to 1 by 4, the leftmost state, in log 1 by gamma steps with high probability. Further, we can show that we hit this state frequently often. In particular, we can hit it at least m times in order of m time steps with high probability. So this was some intuition of how we show our result for 3 or more homogeneous agents, our rate of convergence result. In the paper, we have also extensive simulations of this best response dynamics. On the right-hand side, I have plotted the convergence time with respect to epsilon, log 1 by epsilon at top, and with respect to n at bottom. We can see that for when we are selecting the agents uniformly at random, which is denoted by the blue color, our dependency on epsilon is proportional to log 1 by epsilon, which is as per our upper bound. So our upper bound has a dependency of log 1 by epsilon for convergence time. But on the other hand, our lower bound is log 1 by epsilon, which shows us that we might expect to improve our lower bound to a log 1 by epsilon lower bound, as we see empirically. It also, the bottom plot is with respect to the number of agents, and we see that our analysis is tight. Some ongoing and future work. We have some upcoming results on this line of work. We have improved lower bounds for 3 or more agents. In particular, we have a new tight lower bound which has a dependency of log 1 by epsilon. Further, this result shows that the case between 2 agents and 3 agents, there is a separation, because we have a log 1 by epsilon dependency for 2 agents, while for 3 or more agents, we have a log 1 by epsilon dependency. We also have some rate of convergence results for general homogeneous convex cost, and this uses different techniques and not the best response potential functions and Markov chains we saw in this talk. We also have some results for non-homogeneous regions, where if we extend the best response dynamics to a case where the agents can take small steps towards the best response rather than directly jumping to it, or the best response the agent plays is not with respect to the action of all the other agents at this time step, but with the average of all the previous actions of the agents, then in these cases, for non-homogeneous agents as well, we see convergence. Some open problems are to study convergence of best response dynamics for almost homogeneous agents. where the agents have different cost functions but not too far away. And for this, we empirically see convergence to the equilibrium, but we do not have a formal result. Of tighter bounds for homogeneous agents and convex cost, and learning dynamics where the agents see outcomes but not actions. In particular, this is relevant when the agents only see who wins the game, who wins the contest, but not the probability distribution of each agent winning. So thank you for listening to this talk.